Isothermal processes and path quantities. The word isothermal means that the temperature is constant. We are going to move the system from one state to another without changing the temperature. 1/3 of the mass is removed from the top, grain by grain, in a reversible manner. Here grains are shown like stones for visibility. Here the piston is shown to move with a certain velocity, but such velocity does not develop in a reversible process, as we have seen in the previous videos. The temperature goes down, but heat is supplied in such a way that it compensates the temperature drop. So temperature is constant while moving from state 1 to state 2, meaning PV equals a constant. This path is called an isotherm, the constant temperature path. The work done is the area under the curve. As we have seen in the previous video, while reversing the process, the work done is equal but negative. Now let's see the irreversible path. 1/3 of the mass is removed in one go. Again, heat can be supplied in such a way that the temperature is maintained constant. The work done is the area under this curve. During the backward process, it is not the same. Fine. This is what we have learned. Now let's ask a couple of questions. What about the Q value in these processes? What happens to the surrounding? If we get the answer for the first question, it answers the second question as well. Let's see how. Let's start with the first law. Let's consider only the forward process from state 1 to state 2. The change in internal energy in the reversible process is this. In this, the amount of heat supplied to maintain the temperature constant is Q reversible. For the irreversible process, we can write this equation. Since delta U is the change in a state property, it is going to be the same in both the paths between state 1 and 2. Let's equate the above two expressions. Since we know that work done value is different in reversible and irreversible cases, the amounts of heat supplied in both the processes have to be different. So what is clear now is that unlike U, between the same two states, the work W or the heat Q are not the same. They depend on the process path. This is why they are called path quantities. A small note on notations. Unlike delta U, an exact delta Q does not exist between two states. To indicate this inexact nature, Q is used instead of delta Q. In differential form, small delta Q is used instead of dQ. Now let's consider the forward and backward processes together. That is the cycle. In reversible cycling, if the forward and backward processes are in the same path, the work done is equal in magnitude. Therefore, from first law, we can say that heat supplied and extracted are also equal. In irreversible case, the work done in forward and backward processes are not equal, and so the heat involved. Now think about the surrounding. Obviously, the reversible cycle does not disturb the surrounding. Whatever taken is given back, the Q, and whatever given is taken back, the W. In the case of the irreversible process, it is not so. Let's see it in a graphical form for a system and surrounding together. The initial state of system is state 1 and that of the surrounding is state 6. In reversible case, when the system moves from state 1 to 2, the surrounding moves from state 6 to 7. When the system comes back to state 1, the surrounding goes back to the original state. In the irreversible process, when the system goes from state 1 to 2, the surrounding goes from state 6 to 8. When the system comes back to state 1, the surrounding moves to yet another state, the state 9. In the reversible case, the surrounding comes back to state 6. In the irreversible case, it does not. So here is one way of defining the reversible and irreversible processes. A process that leaves no trace of change in the surrounding, if reversed, is a reversible process. A process that leaves a permanent change in the surrounding, if reversed, is called an irreversible process. So one more small thing to notice here. we use green lines for the change in the state of the surrounding. Why? Because usually the surrounding happens to be a huge reservoir or sink, meaning it can give some heat to the system or take heat from the system, but its temperature is virtually unchanged. For example, if the surrounding of a process is the ocean or the Earth's atmosphere, then its temperature doesn't change. Therefore, as far as the surrounding is concerned, heat comes or goes out in a reversible manner. Therefore, the green line. There is another way to classify reversible and irreversible processes based on entropy change, which is discussed in the video titled Second Law of Thermodynamics in this series. See you in the next video.